Both oxymercuration demercuration sequence and the acid-catalyzed hydration of alcohols give us Markovnikov products. And so sometimes we really do have a need to get the anti-Markovnikov alcohol, but neither of those two reactions would work. The reaction that will give us an anti-Markovnikov product is the hydroboration of alkenes. And this is a synthetically very useful reaction as it complements the reaction that we're already seeing. Practically, this reaction is performed with the use of borane or diborane, which is B2H6, which then adds hydrogen in this boron-based fragment onto adjacent carbons. And finally, oxidation removes the boron and puts an OH group in its place to give us the less substituted alcohol. Let's see how does this work. First of all, borane, diborane, is common with this very strange chemical formula. It has two valent hydrogens. They're just apparently two valent because this is a so-called 3-atom, 2-electron bond, which is a way for boron to stabilize itself with the smaller possible number of substitutions and to avoid its sextet-like structure. And this diborane decomposes into borane, which is just BH3. It's an equilibrium. Borane is a gas and it's pretty corrosive, so you will often see this as combinations of BH3 times CHF, which is a solvent, of BH3 times diethyl ether, and these are just various ways of stabilizing the borane structure. But regardless of which form of borane we choose, one thing that we must realize is that in borane the polarization is slight, but it has delta negative hydrogen and delta positive boron. And so the electrophilic character here really lies mostly on boron. So now if we look at the mechanism of this reaction, which involves boron's coordination on double bond and the formation of this four-membered ring structure where all bonds are part formed and part broken. Then we'll have a CH3 group here and hydrogen here, and the delta minus here will be on hydrogen and delta plus will be on boron. Accordingly, the hydrogen will coordinate to the more cationic center, and this will be the tertiary center, which would stabilize cation better, and this will be the delta minus. So you can see what this is leading to. In the transition state now, hydrogen gets transferred to the more substituted carbon, while boron remains on the less substituted. Now this is the first example of this so-called four-membered transition state, which is very, very well organized transition. What happens next is that we take this alcohol and then we oxidize it, and so oxidatively remove this boron. The way we do that is through the use of hydrogen peroxide, H2O2, and sodium hydroxide, which gives us the desired alcohol. Now, one needs to realize two things. First of all, this BH2 group is able to act as a borane itself, and so one molecule of borane really can act on three different molecules of an alkene. And the other thing is we need to understand here is to see how does this oxidation work. And so the first step in this oxidation reaction is reaction with the sodium hydroxide and hydrogen peroxide. We should take this away and give us HOO minus plus water. And now this will attack boron to coordinate to it and give it again in the octet. Boron will be negative here. And the next step is the movement of this R group over here and elimination of HO minus. So this is the migration from boron, which gives us, eliminates HO minus and gives us this piece. Now this would be a borate ester. And this borate ester is back attack with hydroxide to eliminate the alkoxide, which is then protonated to give us our final alcohol. So this is how this final oxidation step works. Now, because of the highly organized transition state, which keeps these things in a four-membered ring arrangement, this reaction is stereospecific. So if we have, say, a hydrogen here and a metal group here, then the first step will be coordination of boron to give us on top hydrogen, and here CH3. And now this would lead to the hydrogen here, metal group here, boron on the bottom, and hydrogen on the bottom. So importantly, boron and hydrogen added to the same side of the ring. Okay? As we do the oxidation with H2O2 and sodium hydroxide, what you can see from this mechanism is that the reaction really doesn't involve carbon at all. The first step takes place on boron. The second step takes place on oxygen, but with the movement of carbon. The carbon doesn't change much in this step, so there is the retention of configuration here, which means that the final alcohol will also have the cis arrangement of the added groups, in this case oxygen and hydrogen. To summarize this, hydroboration is a very useful reaction. It occurs mechanistically through a four-member transition state, and it's useful because it gives us anti-Markovnikov products in stereospecific fashion, which is something that no other reaction so far was able to provide. So this now allows us to use alkenes in a very powerful fashion to create both Markovnikov or anti-Markovnikov products simply by the choice of reagents we use.